Hello everyone, I'm Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So today we will be discussing assignment 7 and the contents of week 8. Let's proceed. So just to go over the contents of week 7 prior to solving the assignment 7. So we've studied till now we discussed longitudinal stability and control. Longitudinal control is brought about by an elevator. Elevator is on the vertical tail. So the lift produced on the vertical tail produces a moment above the hinge. So if this is your horizontal tail and this is your elevator, a lift. So this is the hinge point and this is the center of pressure at which the forces are generated. So if there is a lift generated at the center of pressure, there will be a moment, a hinge moment about the hinge. Okay, so this is given by this hinge moment equation where CH corresponds to the hinge moment coefficient, and a linearized model of this hinge moment coefficient is given below in this equation, similar to the linearized models that we developed for CL and CM. Okay, so here the terms, the CH alpha T, CH delta E, CH delta T, they are all negative. Okay, so we can see that here when there is a lift generated at the center of pressure. So suppose if your horizontal tail sees a positive angle of attack, positive alpha T, change in alpha T. So there's a positive alpha T, the lift produced at the elevator produces a nose down moment. Okay, so your CH alpha tail will be negative. Similarly, when you deflect your elevator down, when you deflect it down, that is delta E positive. So you have positive alpha T, here you have positive delta E. Again, the lift produces a nose down moment above the leading edge, okay, about the CG of the aircraft. So this again contributes to CH delta E negative. Similarly, CH delta T is also negative. So these three quantities are all less than 0. They're all negative, okay. Now we come to this float condition. Float condition is where your elevator is left to float free when the stick is not fixed, so it's left to float free. At what angle will your elevator float in such a condition? When it's floating freely, where will it rest? It will rest when the hinge moment is 0. So we take CH equal to 0. Applying CH equal to 0, and for this case, assuming CH naught and delta T, that is assuming there are no trim tabs and CH naught to be 0, your delta E float will be obtained by this expression. Setting this to 0 and assuming delta T is 0 and CH naught is 0, you get your delta E float equation like this. So this is the angle at which your elevator will float freely when subject to angle of attack. Now we know that this quantity is negative and this is also negative. So this overall term is positive. Now what that means is for a positive angle of attack at the tail, you have a negative delta E float. So when the tail is subject to a positive angle of T, like this case, your freely floating elevator will be floating upwards. Negative delta E means where your elevator floats upwards. Okay. So when subject to a positive angle of attack, your elevator will float up. Okay. Elevator will float up. That is delta E negative. Okay. That is the delta E float. Okay. Now the other condition that we saw here is the relation between the stability margins of the stick free condition and stick fixed condition. So DCM by DCL is the amount, is a measure of stability, like the stability margin. Okay. So now we know for a stick fixed case, like we've seen before, this quantity is negative for a stable aircraft. Okay. This quantity is negative. Now let's look at the other term, the second term. VH is positive, the tail efficiency factor is positive, CL alpha tail, CL alpha wing, both are positive. This entire thing is a positive quantity less than 1, right? Tau tail control surface effectiveness parameter is positive. These two terms are negative, so this is also positive. That means this entire term is positive. Okay. So we know that anything that contributes towards a positive DCM by DCL is destabilizing in nature. Now this first term is stabilizing in nature, it's less than 0. And this is a positive quantity that is destabilizing. So what we know from this is your stability of stick free case is less than stability of stick fixed case. Okay, because it is a large, it has a positive quantity. So this term contributes towards a destabilizing effect. So the stick free case has a destabilizing component towards it. Okay, so now let's move on. Just going over the stick conventions. So pushing the stick forward, like we've seen before, gives you more velocity. Okay, how do you get more velocity? How do you maintain more velocity and trim? You have to reduce the CL. How do we reduce the CL? We reduce the angle of attack. How do you reduce the angle of attack? You deflect your elevator down. Okay, we've seen, again, this is your horizontal tail. When you deflect your elevator down, a lift is produced at the center of pressure of the elevator, which produces a nose down moment, which in turn reduces your angle of attack. So pushing the stick forward gives you more velocity and less angle of attack. Less angle of attack is such that you maintain trim conditions. Okay. Now, we must note that the delta E required, like we've seen, I think in week 4, the delta E required to achieve a certain CL trim is governed by the stick fixed static margin. It is never the stick free static margin. Okay, so that delta E required, that equation will be based on the static margin of your stick fixed case. Okay. Now, there are 3 conditions that are encountered when you leave your elevator to float freely. First one is delta E float is the same as the one that you require. In this condition, the pilot need not apply any stick force, so your FS is 0, right? So next condition is when you are, yes. So next condition is when your delta E float is less than the delta E required. So the angle at which your elevator is floating freely is less than the angle required for achieving a particular CL trim. So then the elevator has to be pushed up. How do you push the elevator up? You pull your stick. We have seen here that if you push the stick, your elevator goes down. So if you pull your stick, elevator goes up. So the pilot has to apply a negative stick force. He has to pull the stick. Okay. This condition is called stick free stable. Now the reverse condition is when your delta E float is greater than the delta E required. Okay. So what happens? It is floating at an angle more than the one that we require. So we need to reduce that angle. How do we reduce the angle? You need to put the elevator down. How do you pull the elevator down? We've seen in the previous case, you push the stick. So you have a positive stick force. Okay. Now the stick force is given by the next 2 equations, where HM is hinge moment, delta is elevator deflection, and these parameters are the moment arm and the area. Okay. Now, while expanding and deriving the stick force, you get this term, this entire term. Okay, so we know that the first term depends on, first term is the only term that depends on velocity. The second term, your CH delta E is negative, CM delta E is negative, DCM by DCL is also negative. So this entire term comes to negative, and there's a negative sign here, so this thing is positive. Okay. Okay. Now let's move on to the questions. This we had discussed in the previous session. I hadn't solved it. This is your assignment 7 question. So the values given to you, they've given you CG location in terms of mean aerodynamic chord. They've given you the weight of the aircraft, the aspect ratios and spans of the wing and the tail. They've given you the mean aerodynamic chord, the tail setting, wing setting angles, aerodynamic parameters of the wing and the tail. And they've also given you the derivatives, the 3 derivatives that we discussed previously with respect to hinge. So we can see CH delta E, CH alpha, this should be CH alpha tail, CH delta tail, delta T. As we had discussed before, they are all negative quantities. You can see that here. Okay. So all 3 of those derivatives, all 3 of those hinge moment derivatives are less than 0 as seen in this question. Now they've also given you some experimental data for stick fixed elevator case and stick free. On this graph, you can see this graph is CM versus CL. Okay, CM versus CL. So the slope that we had discussed before, we see that the slope of the stick free case is much more than the stick fixed case. Sorry, stick fixed case, the slope is more than the stick free case. What does this mean? More slope means more stable. So stick fixed case is more stable than the stick free case. Okay. So this slope is more than this slope. Okay. This is also as analogous to what we've seen before. And the first question is, how do you find the stick fixed neutral point? How do you find neutral point? Neutral point is defined using your slope, DCM by DCL. So this is the equation to find out neutral point. Okay, now let's try to do this. It says stick fixed neutral point. So let's find the slope of the stick fixed line. So that is this line. What is the slope? That is 0.05 minus 0 by 0.3 minus 0.8. It's the first line, okay? Stick fixed is equal to, what is the CG location given in the question? CG location is 0.3. Okay. So that is minus 0.3 plus x bar np. Now when we solve this, what do we get? X bar np is equal to, can someone tell me? 0.3 plus 0.05 by 5, 0.3 plus 0.1, 0.4. So that comes to 40% of mean aerodynamic chord. Okay? Okay. Now the next question is stick free neutral point. You proceed in the same manner. How do you do this? Same equation. So now you, in this case, okay, so it was dCm by dCl is xnp. In this case, it's stick free minus x bar cg. So now you find the slope of this stick free case. So there it will be minus 0.05 minus 0 by 0.3 minus 1 is equal to x bar np prime minus 0.3. Now this value comes to, can someone tell me what is the value? What is it? X bar np is 0.3 plus, what is the value here? Can someone tell me? .0714. That comes to about 0.37. So that is 37% of mean aerodynamic chord. Am I audible? Can someone confirm if I'm audible?
Yes, ma'am.
Can you hear me?
Yes, ma'am.
Okay, okay, thank you. Okay, so the next question was, how do you find the wing area of the aircraft? Now wing area, how do we find it? They've given you the aspect ratio of the wing. So aspect ratio of the wing formula is this. Now they've given you aspect ratio of the wing and span of the wing. Aspect ratio of the wing is 6. Span of the wing is again 6 square. So by S. This is wing. Okay, this entire thing is wing. Now, so your S wing is 6. Right? So 6 square by 6, 6. So it is 6. Next question is, what is the indicated trim airspeed for stick fixed case? How do you find out the trim indicated speed? It's the equation that we've been solving always. Lift, and then for trim case, we have lift equal to weight. So W equal to half rho V square SCL. And W is given as, so now we have to find out V trim. This is V trim. V trim is square root of 2W by rho SCL. So that comes to 2 into weight is 700 into 9.81. Density is 1.225. That's given in the question. S we had just found out to be, how much was it? 6. 6. And CL is given in the question as 0.8. Okay. So if you solve this, I believe that you get 48.33 meter per second. That is your second option. Okay. Now the next question is, they ask you to find out the tail volume ratio, VH. VH formula is STLT upon SC. Now somebody had asked in the forum that ST, that is tail surface area, is not given. Wing surface area was also not given. We computed it. How do we compute it? We take aspect ratio of tail is span square of tail by ST. Now aspect ratio of tail is given as 4. Span of tail is 2, so 2 square, and then S tail. So S tail comes to 1. Now you substitute all those values in your VH equation. So that's 1. LT is, how much is LT? 6.5. Your wing area was 6. Mean chord is 1.2. This comes to, you just calculate and tell me the value. 0.5 divided by 6. Comes to 0.902. 7. That is the third option. Okay. Now we go to the next question. We have to find out Cm delta E. Cm delta E, we have the formula that's given to us directly, the first one. But now what we see here is the CL alpha tail. CL alpha tail is 3D. It's about the wing. So CL alpha of the wing. But what is given to you in the question, it says lift curve slope of airfoil. Okay, wing and tail airfoils. So that is 2D value. We need the 3D value. How do you relate 2D and 3D? It's using this equation. Now we have to find out the CL alpha tail 3D. Okay, so we start with this. CL alpha tail 2D is given in the equation. So they've asked you in per degree. So we'll retain the units as per degree. It's already given in per degree. Okay. 1 plus CL alpha tail 2D is 0.1 by pi is 1. Aspect ratio of the wing is 6. Okay, I think just a second. Just a second. Okay, so what we need to remember here is that this term, this second term of the denominator is valid, is a dimensionless quantity, and it's valid only if, so it's valid only if your CL alpha 2D is in per radian, because your all the other things have to be dimensionless. Okay, the entire term has to be dimensionless. It's dimensionless only if your CL alpha 2D is represented in per radians. But the value given to us is in per degree. So we need to multiply a 57.3 here. Also, this aspect ratio, this is CL alpha of the tail. So aspect ratio of the tail needs to be taken. That is 4. Okay. So now if you solve this, how much do you get? Can you tell me the value? Sorry, 0.068. Okay. Now you substitute this value into CL alpha tail. So you get Cm delta E is equal to minus. Efficiency factor is 0.9. It's for the tail. Okay. All of this is for the tail. VH, we had calculated how much was VH? 0.903. 0.903. CL alpha tail is 0.068. Now they've asked you in per degree. So this value is already in per degrees. Okay. If there is any confusion regarding the units, just let me know. And then you have tau. Tau is 0.4. So the final value comes to about minus 0.022. Okay, so that is this option. Okay, now we go to the next question. If the airplane was to be trimmed at indicated airspeed of 200 km per hour, find the tab setting required for the new CG location. That is 20% of mean aerodynamic chord. Initially, your CG location was 30%. Now it's at 20%. So that is what we need to keep in mind here. Now, how do you find the trim tab setting? So your equation for stick force is this. Stick force is this. How do you find the trim tab setting? What is trim? Trim is when your Fs is 0. If you set this to be 0, you can find out the trim tab setting from this quantity. Now setting Fs 0 gives you this trim tab setting. Now what are the quantities that we don't know in this thing? We know all of the quantities except for A and dCm by dCl free, because your CG location has now changed. Okay, so find out A. Let's find out A. CH naught is, how much is CH naught? CH naught is 0. CH alpha is minus 0.005. Alpha naught, how much is alpha naught? Alpha naught is minus 2. Wing is 0. Tail setting angle is 2. They're all in degrees, okay? And this CH alpha is in per degree, so there is no conversion required here. And your CH delta E is how much? Minus 0.007. And delta E is how much? 3 degrees, right? Right. So can you compute this value and tell me? Can you just compute the value quickly and tell me? Okay, let me only calculate it. Comes to now this new DCM by this CG location has changed. So your DCM by DCL new, okay, CG location is 0.2 and your stick free neutral point that we had calculated earlier was what? Was 0.37, correct? So your new DCM by DCL free because of change in CG location is minus 0.1714. Okay, so now we have this value and we have A. Substitute these two quantities and you get your delta T. So substitute this and this. This is your A, it goes here and this goes into here. Okay, when you substitute, how much do you get? Just substitute all the values. Okay, so 2, weight is 700, right? 9.81 by surface area of wing. S of wing was 6. Yeah. And 1 by 1.225. Velocity, what was velocity given in the question? 200. Okay, you need to convert the 200 kilometer per hour into meter per second. Okay, so that comes to 55. This 200 that is given in kilometer per hour, you need to convert it into meter per second. Okay, so that means that much. 1 by ch delta t is minus 0.03. Then ch delta e is, okay, let me just erase this. Just write it clearly. Okay, so your delta tail is 2 into weight. Weight is 700 into 9.81 by this is 6. 1 by 1.225 into VI. You need to convert the 200 kilometer per hour into meter per second. That comes to 55.55 VI square into 1 by CH delta T is minus 0.003 into CH delta E is minus 0.007 by minus 0. Delta E. CM delta E. How much was CM delta E? We had just calculated CM delta E minus 0.022. 0.022 into this value 0.1794, right? 1714, sorry. 1714 minus A 0.02 by CH delta T minus 0.03. So the final tap setting angle comes to 3.859. Okay, delta T is 3.859. That is the third option. Okay. Okay. Next question is calculate the DFS by DV for CG location of 20% mean aerodynamic chord. Now CG location is same as the previous question, the new one, not the one given in the original question. Okay. So DFS by DV, we have this formula. All the terms are known there. This DCM by DCL is the new one, which we had calculated in the previous question. So DCM by DCL 3 is, how much is the new one? Is minus 0.1714. Minus 0.1714. Okay. The only unknown quantity in this equation is K, that we calculate using this equation. That is minus G. G is given in the question as 1.5. SE is 0.5. That is the elevator surface area. CE, elevator chord 0.25. That is this value CE. And efficiency factor is 0.4. Efficiency factor is 0.9. Sorry. Okay. Substitute this term into this K and this DCM by DCL free here. So your dou Fs by dou V comes to comes to? Can you hear me? Okay, just a second. Where were we? Okay, yeah. Dou F by dou V comes to? Okay, so I'm just going to write the final answer, 0.37. So that is this one. Okay, now the next question. Okay, so we go on to the week 8 contents. Week 8 contents moved on from static stability into dynamic stability. Okay, so we'll just briefly summarize static stability for the three directions. Static stability for longitudinal case was Cm alpha 0. So we required for longitudinal static stability, you required Cm alpha to be less than 0. What was Cm alpha? Your graph between Cm and alpha was negative. So this was what is required for longitudinal static stability. And Cm not positive was to ensure that we can trim the aircraft at a positive angle of attack. Okay. Now for directional case, similarly, you had Cn beta. Instead of Cm alpha, you had Cn beta. It is Cn versus beta. For directional stability, we required it to be positive. Okay. Now we usually trim the aircraft in the directional sense at beta equal to 0. So it passes through the origin. Okay, Cn beta positive. Similarly, for the lateral case, you have Cl beta less than 0. These are the three conditions for the three directions. This is for longitudinal, this is for directional, and this is for lateral. Okay. What are the main contributors towards these stabilities? In the longitudinal case, you have horizontal tail contributing towards stability. In the directional case, you have the vertical tail. And in the lateral case, you have the vertical tail, a high wing configuration, and if it's a low wing, a dihedral angle. So these were the three main contributors towards lateral stability. Okay. Now this summarizes your static stability. Now we go on to dynamic stability. What is dynamic stability? It takes into account time. So how your aircraft went perturbed.
Ma'am,
Yes.
I have one question.
Yes.
An aircraft with low wing is destabilizing for lateral stability.
Yes.
It is true or false? Like, can you explain?
Okay. Okay. One second. Okay. So this was your low wing. I'll tell you the high wing condition first, and then we'll go to low wing. Okay.
Okay.
High wing was this one. So when you roll towards the right, so suppose it rolls towards the right like this. Okay. So the oncoming wind. So this is the front view. Okay. So when the oncoming wind hits your high wing over here after it rolls right, there is a restoring moment created. Okay. So the force is produced in this direction. This is the V, relative velocity V, and force lift is produced in this direction. So it produces a restoring moment. So it turns the aircraft back to the equilibrium. It tends to turn the aircraft back to equilibrium. Now, if we take low wing, so this is your low wing configuration, and you roll same towards the right. You roll, it comes like this. Now the oncoming wind is again, it's hitting the aircraft here. Okay, so it's at that angle. It's hitting the aircraft here. The lift is produced downwards, and it tends to roll the aircraft further away. That's not restoring movement. It's rolling the aircraft in the same direction. Okay.
Okay.
Okay. So the difference, I mean, the benefit of dihedral, I think Sarah has explained in the video. So if you have a low wing with dihedral, when the same thing happens, when it rolls towards the right, there is one component of the oncoming velocity. So I think it's V sine of the dihedral angle, which acts in the restoring sense, which is why dihedral angle contributes towards restoring moment. So dihedral angle gives you a lateral stability, but a simple low wing is not stable in the lateral sense. Okay.
Okay.
Okay. Yeah. So dynamic stability is when the time comes into play. So when the aircraft is perturbed, how it stabilizes after some given time. So it oscillates and comes to equilibrium. That is dynamic stability. The four governing equations for a point mass body are given here as derived by Sir in the lectures. So you have the four governing equations. One is, which gives you V dot dv by dt. The other one gives you gamma dot, next to our x dot and y dot. So x and y are the Cartesian components. So how it varies in the x and y direction. This is for a 2D case. Okay. Gamma is the flight path angle. V is the velocity. So these are the four terms. These are the four dynamic like differential equations used to solve for dynamic stability of a point mass system in 2D. So xy direction motion only. How do we solve this? These are simple ODEs. We assume some initial condition and solve it numerically. Okay. Now we go on to so forces and moments for an aircraft. That was a point mass. This is for an aircraft. Okay. So we assumed we took our CL. CL initially was a function of alpha and delta E only. That was for the static case. Now when time comes into play, you have two new components, that is Q and alpha dot. Q is the pitch rate, alpha dot is the rate of change of angle of attack. Okay. So for static case, we assumed angle of attack to be same for that instant. For dynamic, we have an alpha dot. So our linearized general model for CL and CM will also incorporate these two terms now. So you have two new terms, CLQ and CL alpha dot. Similarly, you have CMQ and CM alpha dot. Now, why are we doing this? We should have ideally taken CLQ into Q. But why are we doing that? Because Q is not a non-dimensional term. So all the other terms, alpha was radians, so it is non-dimensional. Delta E was in radians, again non-dimensional. But Q is the pitch rate, it's radian per second. That is not non-dimensional. So we take this QC by 2V to ensure that that term is also non-dimensional. So in this case, your CLQ would be dou CL by dou QC by 2V. Okay. So your CLQ, this CLQ is this value. Similarly, you have for CMQ. It's only to ensure the non-dimensionality of that term. Its physical significance would be the same. There would be no change. Now we go on to what happens when the aircraft is subjected to a pitch rate Q. So due to Q, what happens? Due to Q, there is an angle of attack. There is a change in the angle of attack at the tail. This should be delta alpha tail. So there is a change in the angle of attack at the tail. How much is the change in the angle of attack? Approximately, it is QLT by V. LT is the moment arm. Okay, Q is the pitch rate, V is the velocity. So the approximate change in the angle of attack is QLT by V. Now, due to this change in angle of attack at the tail, there is a lift produced at the tail. So your horizontal tail is here and it's subjected to a delta alpha. There will be a delta L produced on the tail. Okay. So this delta L is derived as this equation. Again, the QLT by V, that term comes into play. Now, when we solve for CLQ using this delta L, we get, so CLQ was what? Dou CL by dou QC by 2V. Okay. This was CLQ. Now, when we solve it for the change in lift produced due to change in angle of attack due to Q, we get CLQ to be this value. We do a similar analysis for the moment. So when you have a delta change in lift at the tail, you have a change in moment produced, change in the pitching moment. So that change in pitching moment is given by this equation. There is a negative sign because this positive delta L produces a nose down moment. So positive delta L produces a negative delta M. So this M has to be negative. That's why you have a negative value there. Similarly, you find out C and Q, and that is this value. Now, what we can understand from this is we compare it to a spring mass damper system. Now, we studied that CM alpha was analogous to K, that is stiffness. So in this case, your X is X dot. So X dot in this case would be like Q, and X would be like alpha. Okay. So alpha, it's not the exact same thing, but it's analogous to that. So what contributes towards stiffness is the CM alpha. CM alpha into alpha is what this term represents. CM alpha into alpha. And this term is dynamic. So you have CMQ into Q. Okay. So X dot is similar to Q. X is similar to alpha. CMQ is similar to C. That is CMQ is analogous to damping. C. CM alpha is analogous to stiffness. Stiffness K. Okay, so that is how it compares to a traditional 2 degree of freedom spring mass damper system. CM alpha is the stiffness and CMQ is the damping. The state variables x is similar to alpha, x dot is similar to pitch rate q. Okay. Now, what are the forces that come into play when we consider dynamic stability? The forces that act on an aircraft are aerodynamic, gravitational, and propulsive. Aerodynamic are what? Your lift, drag. Propulsive is thrust. Gravitational force is the mg, the weight that acts on the aircraft. For our case, we consider the gravity g to be constant because it is our analysis is for a short period of time. Okay. So here we consider g to be just a minute. So g is constant. And your aerodynamic forces depend on relative airspeed. Relative airspeed is v relative. Okay, so depends on v relative. It's proportional to v relative. Propulsive force is how much thrust you apply on the aircraft. That is thrust. Now we also discussed the two frames of motion. So our two frames of motion are inertial and body. Body fixed. Okay. So if your aircraft is given such like this, you have your x. I'm representing the body fixed axis with b, so xb. You have yb in this direction and your zb in this direction. Okay, so as the aircraft moves, these frames, these axes move with the aircraft. So that's why it's called body fixed. Inertial reference frame is something that is fixed in space. So what we consider for our case is the earth fixed inertial frame. It is not actually an inertial frame, but due to our short time span of analysis, we can assume the earth fixed frame to be inertial. The earth fixed frame is, okay, so let me just say. Okay. So here, sorry. Yeah, it's fixed. Earth fixed frame is what? It's fixed to the earth. It moves with the earth. So in the real case, it is not inertial. But for your short time span, that is the time span at which you're analyzing your dynamic stability, is so short that we can ignore the angular acceleration of the earth. So we can assume that the earth fixed frame is fixed. So we can assume it to be inertial. Why we need to do this analysis? Because our equations of motion, that is Newton's F is equal to ma, is valid only in the inertial frame. Okay, it's only valid in inertial frame. So we need to do this entire analysis in the inertial frame. Your two equations of motion that represent dynamic stability, the dynamics of the motion of the aircraft, are these two equations. That is the force and the moment equation. Force equation, it comes from your Newton's law of motion, F equal to ma, that is mdv by dt. We consider mass to be constant. So you're the F equal to ma, that is considering, so it is basically dm by dt plus v mdv by dt. Now your dm by dt is considered 0 because we assume that in that short time span, the aircraft's mass remains same. So your final equation becomes mdv by dt. Okay. Now this v is not, so v is what? It's the velocity of the center of mass plus the velocity of your, if it's a rigid body, so some point on this body, if there is some incremental mass delta m here, so the rate of change of this from the point center of mass, this is r. Okay, so rate of change of that velocity of that point is also considered here. So after solving it, finally we get this equation, and we know that sigma r dm, since your axis is fixed at the cg or cm, center of mass or center of gravity, since your axis is originated, your body fixed axis originating at that point, this r dm goes to 0. So your final F becomes m dvc by dt. Okay. Similarly, your moment equation is dh by dt and you get this final term. And again, this term goes to 0. Sorry, first term goes to 0. This term goes to 0 as r cross vc for a axis in an axis that is fixed at the origin would be 0. Okay. Okay. So your final equation would be m is sigma r cross omega cross r. Okay, these are the two equations that govern the dynamics of your aircraft motion. Now we'll look into the questions of week 8. Force F is given. It's acting on a particle located at the vector position R. What is the torque about the origin? What is the equation for torque? Torque is
force into distance.
yes.
So perpendicular.
So torque is force. Sorry, it's R cross F.
Yeah. Sorry. F cross.
That's R cross F. R here is 3I plus 5J cross I and 3J. Okay. When you do this cross product, you can do it the way sir showed. IJK, you have 3, 5, 0, and you have 1, 3, 0. When you do the cross product, you only have components in the K direction, which is 9 minus 5K. So it comes to 4K. Okay. So that is your final answer. That is 4K, the first one. Yeah. So units are important. 4K Newton meter. Now, when you they've asked you to talk about the origin. So the R vector was the position 3I plus 5J minus 0, 0. So when you have it about any other point, you have to consider that. So your torque is R. So this R minus the point. So I'll just take it as P minus the point. That is your R vector cross F. So it is 3. Your P vector is 0I minus 6J. Okay. So you have 3 minus 0 minus of, sorry, you have what? Plus 5 minus 6 plus 6 J. This is I. And you have cross F is same, I plus 3J. Similar to the previous case, we take IJK. I here is 3, 5 plus 6 is 11, 0. Here you have 1, 3, 0. When you do the cross product, you have 9 minus 11 and only in the K direction. So you have minus 2K. So this is minus 2K Newton meter. That is the fourth option. Now the next question is, the position vector of a particle of mass 5 kg is given as a function of time. The position vector is R is 6I plus 5tj meters. What will be the angular momentum of the particle about the origin at time 10 seconds? So what is the angular momentum? H is equal to R cross P, right? So R is given to you. P is what? P is mv. Okay, and what is v? V is rate of change of R. So R dot, that is dr by dt. So R is given to you. So that is differentiation of R with respect to time. Only the J component has a time t variable. So you have 5J. Okay, 5J meter per second. You substitute this value here. You get 5 into 5, 5J meter per second. You have 25, it's kg meter per second. Now this value you substitute here. Okay, it's 25J, don't forget the J. So it's R cross P. R is 6I plus 5tj cross P is 25J. Now I cross J, J cross J is 0, I cross J is in the K direction. So 6 into 25 is 150K. and joules per second, joules second. Okay, so this is your value. They've given you at time t equal to 10 seconds, but this, your h vector does not depend on time. Time was in this quantity, but that term becomes 0. So j cross j is 0. So it becomes 150 joules second. This is the option. Now at any time, it would still be the same value because your h vector does not depend on time at all. So the next question asks you at time 20 seconds, it would still be the same value. You will do the same calculation and it will give you the same 150 k cap, joule second. The last question is, non-dimensional value for change in lift coefficient due to pitch rate is. So change in lift coefficient. So what was that? The CLQ into QC by 2V. Okay, CLQ was what? It was DCL by D QC by 2V, right? So I believe that the option is this, but it should have a QC by 2V, okay? But this is the option. So your equation was CL equal to CL naught plus CL alpha into alpha plus CLQ into QC by 2V plus the other terms. But this is the term that contributes, that is the DCL due to pitch rate. So this is the term, CLQ into QC by 2V. I will just check this up, but I believe this is the right answer. Okay. With this, I think we finished the questions. Yeah, we finished the questions. Do you have any other questions or any doubts?
Ma'am, actually, in the dynamic part, we derive a lot of questions, right? And then we linearize that and make in second order term, right?
Yes.
Hello?
Yes, I can hear you.
Yeah, so means we do the perturbation to make linearize the equation only to get second order.
Yes.
That is the thing, right?
Yes.
Yeah, so actually I have confusion means why we are doing.
Okay. So you're right about that.
And after making this in second order,
Huh.
we go to the control part.
Yes.
Lambda and all.
Yes.
And ma'am, in this course, that control part also will be taught, or
I'm not
like
very sure that, but we still have 2 weeks left. We'll see.
okay.
Okay. Yeah. So the class that is we should have ideally done week 9 today, that will be taken on Sunday from 6 to 7 p.m. Okay.
Okay.
So do you have any other questions?
No more. I'll ask on the next class. Actually, I have not done all the questions.
Okay, yeah. So Sunday we'll have another session. You can ask your questions during that time.
Okay.
Okay. So I think we'll end this.
Thank you.
Yeah. Thank you.